Here on the board we have some notes that you can pause the video and copy down. All right, now you're done. So today we're going to be talking about something called hybrid orbitals. And hybrid orbitals give us a really well opportunity to understand shapes of organic molecules. If you understand the hybridization on various carbon atoms in a molecule and what that all means, then you're going to have a lot better chance at understanding the general shape of the molecule, and that's what we're going to do today. So we're going to introduce the topic by seeing a new way to think about orbitals, combining some of the old things we knew with some newer things. This would fall under the general category of molecular orbitals. You don't need to write that down, sometimes referred to as MOs. This is one way to classify molecular orbitals. And so let's just go back and review what we know about valence orbitals. We know that valence orbitals come in S, px, py, and pz forms. The s's are sphericals. The p's are dumbbell shaped and aligned along different axes, the px axis, the y axis, and the z. This is coming in and out of the board. Try to visualize that coming in and out of the board. It's kind of hard to draw. If you were to actually look at it, it would just look like a circle, because the back end would be blocked by the front end, but I kind of drew it at an angle so you could tell that it wasn't just an S. And what hybrid orbital theory does is, rather than treating those orbitals as separate entities, we realize that all of these electrons are working together and kind of combined into one energy state by their situation. And whenever bonding occurs, they sometimes will, whenever we satisfy an octet rule, whenever we do this, when we do that, when we add orbitals together, they sometimes take on new shapes. And so a hybrid orbital, just like hybrid anything else, if you have a hybrid of two animals, you basically cross their DNA, right? You mix them together to make a new thing, a hybrid strain of corn or whatever. That's what we're doing here. We're taking the S and the 3p orbitals and we're adding them together to make this new kind of orbital that we're going to call the Sp3 orbital. And the Sp3 orbital is one of the nice things about all of these orbitals is that I'm not going to introduce you to any new shapes today. They're all shapes with which you're already very familiar. What do we call an Sp3 orbital shape? Am I that bad at drawing? Come on, bail me out here. Little tripod with something coming off the top. Back when we did B-separ theory, what's that called?
Upside down umbrella.
No one's seen this before in their life?
Is it a T word?
Yes.
Triagonal.
No, other T. Tetrahedral, yay! That's a tetrahedral shape with the 109.5 degree bond angles and all the things we already knew. So one way to think about a tetrahedron is it's what you get if you add up mathematically using Schrodinger's equations and whatnot, the S and the three different p orbitals to get this Sp3 shape. Okay? Now, the second kind of hybrid orbital is exactly the same idea, except instead of taking all the S and all the P's, what we do is we basically take an S, a P, we throw them all into a blender and we get out an Sp3. Here we're going to do the same thing, but the ingredients are different. We're going to throw in an S and we're going to throw in a PX and a PY, but we are not going to put the PZ into the blender. It's going to remain separate. So we're hybridizing an S and two p orbitals, not all three of them. And that results in this shape here, which what I've done here is I've left the Sp2 as the black hole lines, but this PZ that did not go into the blender, that's kind of left over, it's still there, we just didn't put it into the hybrid orbital. I've left that as blue, and I've actually made it a dot. I don't know if on the video if you can tell whether it's a different color, but this is, maybe should have used green or something, but that dotted line is this PZ orbital. And the term we give for that one that did not go into the hybrid is it's an unhybridized p orbital. It's unhybridized. We didn't throw it into the mix. It's still its own thing. So here is an Sp2 orbital with this unhybridized P. So what shape is an Sp2 orbital, Jeffrey Baxter?
Triagonal planar.
Oh, you go, girl. I'd clap, but I'm holding coffee. Yes, that's correct. Trigonal planar. So the bond angles here would be, what's the bond angle on a trigonal planar? Starts with a 1, ends with a 20. Good. These are 109.5 there. And finally, the last type of hybrid orbital is the Sp orbital. We're going to throw an S and just one of the P's in to make a hybrid orbital. That is this black thing here, this whole black line, which basically looks like a bigger P orbital, doesn't it? But notice that now we have not one leftover unhybridized P orbital, but 2. And that kind of gets kind of messy there whenever you're bad at drawing like I am. I've tried to put 2 dotted lines. Here's my Py right here, and here's my Pz left over. And so those are what hybrid orbitals are. And now what we're going to see is we can use this basic idea of how these things look and what their angles are in order to predict the shape of an organic molecule.